All right, everyone, welcome to the first New York Combinatorics seminar of the semester. We're happy to have Sandra Kingan, who's going to tell us about deletable edges in three connected graphs.
Thank you, Deepak. I really appreciate this opportunity to give this talk, and I wanted to do it virtually, even though we could have met at the Graduate Center in the hopes that I could post a nice talk. Let's see. This paper just appeared in Discrete Math, and it was done quite some time back. And I thought that now that it just appeared, might be a good time to give a talk. So we will go through minus and higher connectivity, and I will go slow in the beginning in case there are any graduate students here, or hopefully for future graduate students who will be listening to this. Edge additions and vertex splits, Wheel's theorem, splitter theorem, H-deletable edges, the main theorem in this paper, and then some applications. So the first thing I want to note is that the graphs in this area have parallel edges and loops, and graphs without parallel edges and loops we will call simple graphs. And when you're talking minors, you always can get parallel edges and loops. And therefore, when we are talking about what everybody else thinks of graphs, we will say simple graphs. Okay. A graph H is a minor of a graph G if H can be obtained from G by deleting edges and any isolated vertices formed as a result, or contracting edges. Now, deleting edges is very clear. So in this graph G, where my mouse is, you have E, and you remove edge E, and you have this. You leave the two end vertices intact. Contracting edges. So imagine an edge like a string, and you identify the two end vertices, so you get kind of a loop, and you delete the loop. Or you can just think of it as this edge just kind of squishing down, forming this vertex. You will notice that I have deleting edges and any isolated vertices formed as a result, is because if you delete a bunch of edges, you might end up with isolated vertices, and they should be removed. Now, those isolated vertices can also be just removed by contracting edges. So it would be fair to also say H can be obtained from G by deleting or contracting edges. But I wanted to make that a little bit clear. And a minor is a proper minor if it is not the empty set or just G itself. Okay, so let me paint a picture of connectivity for you. If G is a connected graph, right? Imagine a connected graph. A set of vertices whose removal disconnects G is called a vertex cut, right? Imagine a connected graph, and you pull out a set of vertices, disconnects G. We have that little bit over here, or results in the trivial graph, simply because we have to account for Kn, the complete graph, and you'll see in a moment. The connectivity of G, kappa G, is the size of the smallest vertex cut. So the smallest vertex cut in your graph is the connectivity, and we say G is K connected if kappa is at least K. So all of that, in short, G is K connected if at least K vertices must be removed to disconnect the graph. If you're thinking about Kn, then you remove n minus 1 vertices, and you've got the trivial graph. So just for that sake, we have an extra clause over there, which you can forget about. All right. And then some people emphasize, well, their graph has to have at least K plus 1 vertices if you're deleting K vertices. So the focus here is three connected. A graph is three connected if at least three vertices must be removed to disconnect G. And I like to say it this way: by convention, K4 is three connected. So here are some examples of three connected graphs. They're the standard examples. At least three vertices must be removed to disconnect G, all right, in these examples. And that's the prism graph that we'll be talking a lot about. And our notation for wheels is maybe something slightly different than you're used to. The wheel has n vertices, but we will label the spokes as 1 to n minus 1. So we will always refer to the wheel as W subscript n minus 1 instead of Wn. And that is to match up with the matroid terminology, where the wheel is denoted as WR, where R is the rank. The rank in a graph is n minus 1, size of a spanning tree. So Whitney in 1932 proved an equivalent version of Menger's theorem, which was done a few years earlier. And Whitney's theorem is a graph is k-connected if and only if there are k pairwise internally disjoint paths between every pair of distinct vertices u and v, and k pairwise internally disjoint paths sound exactly what it says, as in you have u, you have v, and you have k paths between u and v, and they only have in common u and v. So you can get a nice little corollary of this that I'd like to publicize a bit. If G is 3 connected, right, then G has a K4 minor. K4 is W3, right, the 3 wheel. That's the complete graph on 4 vertices, is also the 3 wheel. And the proof is very straightforward, just a corollary of Whitney's result. So let U and V be 2 vertices, right? Since G is 3 connected by Whitney's theorem, just move this aside a bit. There are 3 pairwise disjoint paths, right? P1, P2, P3, drawn over here, drawn on the next slide also. Now, one of these paths could be an edge, so we will assume that 2 of the 3 paths have at least a vertex here, X, and a vertex here, Y, right? And then you can actually see how you can just contract everything down to get K4 over here. So think of it very visually. You have 3 paths. One of them could be an edge, but definitely the other 2 will have a vertex and a vertex here. And then you can just squish it down all to get, this is W3 or K4. All right, so every 3 connected graph will have a K4 minor. Those are just the details. Is this clear? Everybody good with this? Right. And from that, right, you get another little obvious corollary straight from that. An edge E in a 3 connected graph is called contractible if G contract E is 3 connected. So as a corollary, we get if G is a 3 connected graph except W3, then G has a contractible edge, right? Everything, all 3 connected graphs can have a W3 minor, right? W3, K4, same thing. So it will, if it's not W3, then everyone will have a contractible edge. And keep in mind in graph theory, if you contract this edge and you get this parallel edge, this graph is still 3 connected, all right? Not saying that it has to be simple, right? Just said an edge is contractible if G contract E is 3 connected, right? So any 3 connected graph except W3 has a contractible edge. All right, let's talk about edge additions and vertex splits. So graph G with an edge E added between non-adjacent vertices, right? And we'll denote it as G plus E. This seems like a reasonable definition, terminology there. I've seen it actually in other places. And that's just G plus E. So you have G over here, the prism, you add an edge like that between existing vertices. Don't make any new vertices. You just add an edge to existing vertices between existing vertices, and that's G plus E. Don't do this because this won't be simple. You wouldn't think of doing it anyway, I'm just mentioning it. And so if G is 3 connected, then G plus E is also 3 connected. All right, so that's edge addition. And now what vertex split is the opposite of contraction, and it's a little bit involved. So let's go through this carefully. And the key difference is that when you add an edge, you're just getting one graph over there, right? You could add, of course, you can add edges between here, and then maybe you could get a different graph, but not in Prism. Prism has just one non-isomorphic edge addition. But let's talk about vertex splits, okay? Now, vertex split by itself, you don't technically need degree of the vertex is at least 4. We're just putting that in so that we can guarantee that our vertex split is 3 connected. So take your vertex V, split it into 2 things, have a new edge F over there, the blue edge. If you look at it backwards, right, you contract V1 and V2 down back to V, right? That's contraction. And in order to preserve the 3 connectivity, we will assign edges to V1 and V2 so that both vertices have degree at least 3. Otherwise, you lose 3 connectivity. You can split a vertex without necessarily doing this, but let's just call this vertex split. All right. Now, we can get a different graph depending on the assignment of neighbors to V1 and V2. And on my next slide, there is an example. Right? So take a vertex, break it up into 2 things, put an edge over there. So these are all the vertex splits of K5. Let me just jump ahead and say they're all isomorphic. But when you're actually calculating them, there's a whole bunch, right? So you can, this is your vertex V. I broke it up as V1, V2 here, right? And I can assign A, B to V1, or AC, or AD, or BC, or BD, or CD, right? So not all of these have to be isomorphic. They are for K5. But you can get many vertex splits from when you split one vertex, many non-isomorphic vertex split. Let me jump back to the previous slide for a moment. The symbol of choice I've used is G.E. There's actually no notation for vertex split in the literature. And so about 10 years ago, I made one up. I decided to call it G circle E. If anybody has a better notation, I'm happy to hear it, and we can always change to a better notation. But in the absence of a notation, we'll use G.E. So that's K5 again. Yeah, they're all isomorphic in this. And by the way, that's the vertex split of K5. When it's drawn like this, it doesn't look like a vertex split of K5, but it is. Now let's look at, now the prism doesn't have vertex split. It's a cubic graph, but the prism with an edge definitely has a vertex split, right? And you can split the red vertex, you can split the green vertex, and you get, after examining all possibilities, you get 3 non-isomorphic vertex splits. Right? So you don't necessarily just get one vertex split, like you get one edge addition. When you split a vertex, here there are 3 non-isomorphic vertex splits. Any questions? Good? All right. Give me some feedback. Everything good?
Sandra, I have a question.
Uh-huh.
When you do the vertex split like that, right? Do we have like the neighborhood of the original vertex that you split? That's the V1 and V2 neighborhoods are disjoint, right? In other words, it's a partition essentially of the original neighborhoods.
Yes, but the neighborhoods don't have to be disjoint. But when you I'm sorry. Yes. So when you take this vertex and you split it into 2,
yeah,
right, then the neighborhoods have to be disjoint.
That's what I mean, right? So in other words, and it doesn't necessarily, like here you've done it evenly, right? But as long as you do the 3 connected preserves, and it doesn't matter, right? If they had a lot of adjacencies, then you could do 1 is 3, 1 is 7 or something or whatever.
Yeah.
Okay, good. Thank you. That's all I was just saying. This is a new concept for me. So I just want to thank you.
Yeah, it is, and it's exciting actually. There's a lot of work that could be done here on vertex splits, and especially if you raise the connectivity to 4 connected. All right, thank you. So now I'm going to go through the Wheels theorem, and I'm going to do 5 versions of the Wheels theorem. It's just such a foundational result by Tutt. It is actually Tutt's Wheels and Whirls theorem. It's a matroid result, and some of this work extends to matroids in the paper, but in this talk, I'm just focusing on graphs. So let's look at the wheel. If you delete an edge, right, you lost 3 connectivity, right? This graph is not 3 connected. If you delete the rim edge, if you delete a spoke, you also lost 3 connectivity. If you contract an edge, right, it is still 3 connected by the graph definition, but it's not simple anymore, right? Here too, if you contract a spoke edge, this is not simple. And Tutt proved that wheels are the only ones where if you delete an edge, you lose 3 connectivity. And if you contract an edge, it's not simple. So this is one version, and maybe the basic version of Tutt's result. Let G be a simple 3 connected graph. Such that G delete E is 3 connected and G contract E is, did I write that correctly? I don't think I wrote that correctly. Let G be a simple 3 connected graph. Then, well, this is the blue statement is the correct one. For every edge, E, G delete E, and G contract E are not simple and 3 connected, okay? So that's the blue statement. Take the blue statement. I think there's something wrong in this way I wrote the first version. Okay, let's quickly get to the next one. Okay, the top-down version. So suppose G is not a wheel, then there is an edge E such that either G delete E or G contract E is simple and 3 connected, all right? So if G is not a wheel, then you can always find an edge E such that either G delete E or G contract E is simple and 3 connected, okay? So every other graph besides wheel has a property that you can delete an edge and get 3 connected. When you delete an edge, it's either 3 connected or not 3 connected. You won't lose simple. Or when you contract an edge, you'll get simple and 3 connected. So let's look at the constructive version. Suppose G is not a wheel again, then there is a simple 3 connected graph G dash such that you can obtain G from G dash by adding an edge or splitting a vertex, all right? So that's the constructive way of saying this same thing. There's such that G delete E or G contract E is simple and 3 connected, or you can grow G dash and get G, or split a vertex and get G. All right, so the top-down chain theorem. Suppose G is not a wheel. Again, I have to exclude the wheels are the only ones where this doesn't work. Then there is a sequence of simple 3 connected graphs. Starting with G, you can do deletion contraction and get down to a wheel. So let me again paint a picture for you. So you start with a wheel with G, and you can do deletion contraction and get down to a wheel, maintaining 3 connectivity throughout, because the wheel is the only family of graphs for which if you delete an edge, it's not 3 connected. If you contract an edge, it is not simple and 3 connected. All right, so that's why simple three connected is there. So and one more version, I think. Yeah. And the constructive version. So if you have G, right, you can start with the wheel minor. It has a wheel, there'll be some wheel minor that it has, and you can grow G from the wheel by adding an edge or splitting a vertex. Let me pause here and ask if there's any questions. And please apologize for having that first version of the Wheels theorem incorrect. Wheels are the only ones where if you delete an edge, it's three connected, or if you contract an edge, if you delete an edge, it's not three connected, and if you contract an edge, it is not simple three connected, right? So we have to understand this before we go forward to splitter theorem, because the main difference between the Wheels theorem and the splitter theorem is that you can replace wheel with any minor h. So this is the version that I'd like to emphasize. So if you have a three connected graph G, simple three connected, it's not a wheel. It's going to have some wheel minor from which you can grow up to G by deleting an edge, or by adding an edge or splitting a vertex. Any questions? No? Okay, let me go forward. So the splitter theorem is, it appeared in 1980 in Paul Seymour's decomposition of regular matroids. And then in 1982, Negami gave a entirely graph theoretic proof of the graph version of it. Splitter theorem holds for matroids also. And then Collard and Oxley extended, simplified the hypothesis a bit. So put these three things together and you get this result, which I think I have four versions of it. So you're starting with G and H, simple three connected graphs such that H is a proper minor, right? And you're excluding wheels, and of course H should not be W3. Then G delete E, or then G delete E or G contract E is simple three connected and has an H minor. So this is the constructive version of that. So if you focus on this line here, then there is a three connected simple graph G dash that has an H minor such that G is G dash plus E, or G is G dash split a vertex. Okay. So you can obtain G from G dash by adding an edge or splitting a vertex.
Sandra, can I ask about the first version? Does this mean there exists an E such that is true? It's not true for every E. Am I wrong?
Yes. Yeah. Yes. Okay, then there is, yes. Then there is an E. Yes. Thank you. There is an E such that G delete E or G contract E is simple three connected and has an H minor. Yes. So splitter theorem, top-down version, and also the constructive version. Yes, Tom, for some edge E, all right? So you have a graph G and you have a minor H, then you can get from the top down, you can go from G to H by deleting or contracting an edge and maintaining three connectivity throughout. And the constructive version if you know that G has an H minor, you can grow from H to G, right? Go from H to G by adding an edge or splitting a vertex, right? This notation here is splitting a vertex, even though it is in terms of an edge, right? So that edge that we added, that's the one that is mentioned here, right? So I'll say that again. So forget about the wheels, right? Starting, if you have a graph G and it has an H minor, right? Then you can go from from G down to H by deleting an edge or contracting an edge and preserving 3 connectivity throughout. Oppositely, you can grow G from H by adding edges and splitting vertices. And a little technicality here, you have H is when you're going top down, you're starting with G, right? And the G, when you finally get down to H, it could be something isomorphic to the H. And here, when you're starting with H and you're growing up, you could get something isomorphic to G. All right. And this works for all 3 connected simple graphs, except for wheels. Any questions? Okay. So let's move on. So let's talk about H-deletable edges. So an edge in a 3 connected graph is deletable if you can delete E and preserve 3 connectivity, right? So this is my prism graph with an edge E over here. If I throw E out, right, the graph that I get is 3 connected. If I throw this one out, right, if I throw F out, the graph is not 3 connected. And the well-known definition of minimally 3 connected, you cannot throw any edge out. If you throw an edge out, you lose 3 connectivity. All right, so a 3 connected graph is minimally 3 connected if it has no deletable edges, right? So we're doing something analogous to minimally 3 connected, but preserving the H minor. So suppose G and H are simple 3 connected graphs such that H is a proper minor of G. And edge E is H-deletable if G delete E is 3 connected and has an H minor. So suppose this is, I have a little question here. So let H be the prism graph. Which of the following graphs have a deletable edge? So the first one, so does it have a prism deletable edge? Yeah, if you throw this out, you have the prism. Does this have a prism deletable edge? No. If you throw out any one of these edges, like any edge, you lose 3 connectivity. This one's minimally 3 connected. What about this one? Yeah, this one has an edge here. If you throw this out, it has a prism minor. This one is much larger and harder to see, and I'll just say, yes, it is minimally 3 connected. Okay, so it does not have a prism deletable edge. And I think I have the answers on the next page. Let's see if I said that right. Yeah. This has an H deletable edge. No, yes, no. All right. And our goal is to get a structure theorem for graphs with no H-deletable edge, and as a bonus, we get a structure theorem for minimally three connected graphs, and that in turn helps us determine, characterize excluded minor classes of graphs. So that's sort of the big picture. Any questions so far about H-deletable edges? Oh, good. Okay. So this is the main version. And if you've heard me giving a talk about the strong splitter theorem in the past, this is a version of that. Is actually, you can get the strong splitter theorem from this result. The strong splitter theorem was published in 2014 by Manuel Limos and myself. It's a Matroid result, and it was expressed in Matroid language, whereas this version is easier to understand. And the other thing about these results is, so a graph sits inside a larger graph, right? Every graph is a subgraph of a corresponding complete graph. That is not the case in matroids in general. So when you're talking about matroids in general, you do not have a constructive version like this. You do have a constructive version for matroids representable over finite fields, because there also every matroid will sit inside an appropriate projective geometry. So the original 2014 paper on strong splitter theorem, the language is very, very different. And this is, it's been 10 years, and, over time, we found an easier way of saying some of this. All right. So exclude the wheels, right? And G has a proper H minor and no H-deletable edge. Right. Then there is a smaller graph, G dash, also with an H minor and no H-deletable edge, such that G can be obtained from G dash by splitting a vertex, by adding an edge or splitting a vertex in a very specific manner. And that specific manner can be visualized here, right? Adding an edge E and splitting it so that EFG forms a triad. What's a triad? Triad is three edges incident to the degree 3 vertices. So the 3 edges incident to a degree 3 vertex, right? And you can add 2 edges and split the vertex so that E1, E2, F is a triad, right? So that's a very, very specific way that you can get, you can grow graphs with no H-deletable edges. Right? So if G has no H-deletable edge, you can find a smaller one that also has no H-deletable edge in this manner. So I know that's a lot. I know that this theorem is not easy to absorb. Maybe the next, the top-down version might be a little bit easier to grasp, but the constructive version is how it is used. How are we doing on time? Yeah. So I don't have to exclude wheels when I write the top-down version, because I can contract a rim element and then delete a spoke and get a smaller one, right? So when I contract a rim element, I get parallel edges and just delete a spoke. So if G and H are simple 3 connected graphs such that G has a proper H minor and no H-deletable edge, then there's a smaller one with the same properties such that G dash is G contract F, or you contract F and delete E, where edges EF are incident to a degree 3 vertex. or you just throw out a degree 3 vertex. So this might be a little bit easier to grasp. So you have a graph with no H-deletable, with an H minor, no H-deletable edge. You can get a smaller one by contracting an edge, right? Or looking at a degree 3 vertex and then contracting an edge and deleting the other edge of the degree 3 vertex, or just throw out the degree 3 vertex. So the proof is not hard. It's definitely not hard. It's entirely in terms of graph theory. And I call it the linking, unlinking argument that I use, which is very algorithmic. And I won't do the proof here, but I just want to say the proof is just about a page. And then in the paper also has the matroid version of this result, and it is very short. So it's a good example of when you look at things in abstraction, you can say things in a very concise manner. I'm actually hoping to make another video where I just do the proof of this theorem, because I think it is quite accessible. Anyway, not here, so I'm going to go on to applications. Okay, so immediate application that we get is a splitter theorem for minimally 3 connected graphs. So suppose G and H are minimally 3 connected graphs such that G has a proper H minor, right? And then you can find a smaller minimally 3 connected graph also with an H minor that is obtained by contracting an edge, contracting or deleting an edge in a specific manner, or just throwing out a degree 3 vertex. And it follows directly from, this. If G and H are minimally 3 connected, then by trivially G has no H-deletable edges. And what I have here is a little note to myself to bring up Dawes' theorem. So Dawes gave an if and only if condition for minimally 3 connected graphs, and he didn't do it in terms of deletions and contractions. He did it in terms of different operations, because he built on Barnett and Grunbaum's operations for growing graphs. And in a paper that appeared last year, we actually showed how to take Dawes' result and express it in terms of deletions and contractions. So slightly different from this. But in the next paper that I'm going to write is going to be an if and only if condition for H-deletable, for graphs with H-deletable without H-deletable edges. And I'm going to use Dawes conditions over there, which I'm hoping would work. This is like work that I'm hoping will, a theorem that I'm hoping will work out. Is I'm going to take this and translate it back into Dawes operations, and then use his if and only if condition to get myself a theorem where I can say G has H-deletable edge if and only if. So it's very closely related to Dawes' work, which is closely related to polytopes. So if I may say one more thing about this, my understanding of this all happened in the 60s. So you had Tutt do the deletion contraction version of these results, and then Barnett and Grunbaum did certain other operations that look very different from deletions and contractions, but they're all equivalent. You can get from one to the other. So okay, we can get a result on extremal graphs with H-deletable edges. It's just a simple induction argument. So let's see, how much do we want to say about it? So if G and H are simple three connected graphs such that G has an H minor and no H-deletable edge, it seems reasonable that it can't have too many edges, right? Just like minimally three connected graphs, you can't have too many edges, it's bounded by 3n minus 9. So it would seem reasonable that a similar result holds for graphs with no H-deletable edge, and sure enough, the size of G is bounded about by the size of H and the difference in the number of vertices between G and H. This was the first result I was able to prove, assuming the theorem that I hadn't actually finished proving. So I think this result dates back several years, but this is when I felt like I had something. And then, of course, I had to prove theorem 1. That was a little bit more. So I like this result a lot. It was how I started this whole paper. Okay, shall we move on? Yeah, so as a consequence, if your graph has too many edges, then it's going to have H-deletable edges, and you can say exactly how many. All right. So now I'm going to use the theorem 1 to do a reproof of a very nice result by Dirac, where he characterized the graphs with no prism minor. And I'm very fond of this result because I generalized it to matroids, and it was my first paper, actually, where I generalized this to matroids. So I'm really fond of this result. And I don't think it's gotten enough credit in graph theory, so I'm trying to promote it a bit. So a simple three-connected graph has no prism minor if and only if, and Dirac told us exactly what's in the class. And graphs that are not three connected, well, you have the trees and you have series parallel networks. Those are not three connected. And the others can be constructed from these graphs by direct sum and two sum. That's a result of Bixby. So in this area, in graph structure, we tend to look at just three connected graphs and higher. And recently, there's been a big push to do structure theorems for four connected graphs, and then try to figure out, characterize excluded minor classes in terms of their four connected members, because most classes have too many three connected members. But I would say this is like one of the first results where you can determine precisely what an excluded minor class is. And here they are, K5 without an edge, right? These are 5 vertices, so they have to be there. Wheels always end up being an exception. And then you have this family, K3n minus 3, right? 3 vertices here and n minus 3 vertices here. Add an edge, 2 edges, and 3 edges. So I like to call this a monarch, because if you know this, figuring all this out is you just have to delete edges. But actually, the way in the proof, it turns out that this one is also very important, because if you know this one, then you can grow all these quite easily. But I don't have a good name for this. And in excluded minor results, we are looking for monarchs, right? We want to say what's in the entire class, not just, the minimally three connected graph in the class. But in all of these results, it turns out that this one is more important. I called it seeds in a matroid paper, but I don't think that's a good name. I think monarch is a good name for this, but I don't think seed is a good name for this. But anyway, the overall conclusion of all this stuff is that if you want to figure out an excluded minor class, you better figure out the minimally three connected members first. And if you can figure that out, then you can figure out everything else. Okay, so now Dirac's first proof is very long, and then on page 26 of a textbook whose name of Bolabash's Extremal Graph Theory textbook, page 26 is a shorter version of Dirac's proof, but this reduces it entirely to proof by picture, even shorter than that. Oh yeah, I forgot that on the next page, I had the big discussion about what I was saying. Monarchs, I'm sorry about that. I should have flipped the page sooner. So I have, these are the monarchs. This is the rank 5 monarchs. The wheels are by itself. And this is the monarch over here. And it's the wheel, the minimally three connected versions are just as important, the first ones, not just the last ones, right? So everything I said earlier is on this page. So I'll just give you a moment to read it. Yeah. Yeah, and if you figure out the minimally three connected ones, then you can figure out the monarchs easily. Okay, shall I move on? Yeah, so proof by picture. So so this is the base case of the induction argument, and you have to check that, the up to isomorphism, these are the only graphs and everything, but we can just that's straightforward. There is so much symmetry in these graphs, it's not hard to actually do by hand. You don't need even software to do this. So the wheel W4, right? And has one edge addition, K5 delete D, that has one edge addition, K5, and you're done. Now, the wheel W4 has two vertex splits, prism and K33. We're throwing out the prism, and we want to know what's left. All right, so you're starting with K33. And it has, by the symmetry of K33, it has just one edge addition. And that one, it has, and then then add another edge, K33 double dash. If you add an edge here, you immediately get a prism minor, so it's not in the picture. So K33 dash has more than one edge addition up to isomorphism. You can add an edge here, or you can add an edge here. But if you add an edge here, it's got a prism minor, so it's gone. And similarly here, the only graphs with no prism minor when you start with K33 is K33 dash, double dash, triple dash. Now, look at the vertex splits of K33. I use the matroid term for vertex splits, coextension. It has just one vertex split without a prism minor. And the theorem one, now without the main theorem of the stock, you would have to do a lot of checking. With the main theorem of the stock, you just have to split this vertex V in this very specific manner. This is operation 2 in the theorem. You can be certain that everything else has a prism minor. And this is operation 3 in the theorem. When you add two edges, you only have to split the common vertex, and you split it in this manner. So it takes what could be a number of checks and says there is only one thing to do. And this one is unique. You don't have to check anything else. Here, because of the symmetry, it turns out to be just one. But this is always just 1. So that's the base case of the induction argument using the theorem. Very little checking to do. All the checking that had to be done in the past, well, actually, there was a theorem buried in there, and that's what theorem 1 is. And then the next thing is the induction argument. Once you understand that, and this is just a matter of saying it, it's a little complicated to say it, but all it is saying that the result holds for one step below, and K3n minus whatever dash has just one vertex split, and K3 double dash has just one vertex split. That's it. So all the computation is gone. There's about a half a page explanation of this, which is just basically saying the induction argument. It comes down to a proof by picture. And as a bonus, there's this nice little result that I was able to extend by Harlan, which, so let's talk about it a little bit, okay? So let G be a minimally 3-connected graph. And a very simple argument gives that E of G is less than or equal to 3n minus 9. And actually, this result is also in Bolobash's extremal graph theory, and a result like that holds for minimally k connected too. All right, so it can be generalized nicely. So if I can work out the structure theorems for 4 connected, then I could generalize also, or attempt to generalize, the higher connected result. But now, as of yet, we don't have good structure results for 4 connected graphs. And if E of G is 3n minus 9, then the extremal one is K3n minus 3. And just a little thing is, why are we going up starting with n greater than or equal to 8, in case you're wondering? Well, the wheels get in the way. Wheels have 2n minus 2 edges, right? So at n equals 6, W5 has 10 edges, and K33 in the prism have only 9, so you just want to get past 6. N equals 7, you have K34 here has 12 edges, but so does the wheel, so then you've got that. And it's past 8, it's just K3n minus 3, and therefore, we have n greater than or equal to 8 in the hypothesis. It's a minor detail, okay? So I was able to find the extremal graphs with 3n minus 10 vertices. I know that I'm just going from 3n minus 9 to 3n minus 10, but, there's a result there, and it just fell out from Dirac's proof. I really didn't have to do anything. It was staring at me the whole time, so it wasn't like I was searching for something. So if you have 3n, the extremal graphs, 3n minus 9 is K3n minus 3, but you can also get the next one, 3n minus 10, if and only if this K3n minus 4 perp. That's what I'm calling it. If you have a better name, let me know. I'm happy to change names. So yeah, the new family is this. Why are we doing n greater than or equal to 9? Just to avoid the wheel that always gets in the way, right? So the fact that you're starting with n greater than or equal to 8 and n greater than or equal to 9 is trivial. So what's the proof idea? Well, if G has a prism minor but no K33 minor, then actually you can show that EG is less than or equal to 3n minus 11, because the first time operation 3 is used is when n equals 8. So in the example where in an example on a previous slide, we saw that. There's a little bit of a detail here, but the first time operation 3 is used when n equals 8, and from that you get that E of G is actually less than 3n minus 11. So case 2, suppose it has a grade 3 minor. Then theorem 3 gives you E of G is less than or equal to 3n minus 9, right? Remember I said that the argument for why E of G is less than or equal to 3n minus 9 is a couple of lines, and here they are. And we want to prove that if it has 3n minus 9 edges, then you get K3n minus 3, which is what Holland did. And if you have 3n minus 10 edges, then you get just one family. Now, you might wonder, what about 3n minus 11? Too many families. I think it's doable, but it's just not seeing the pattern as yet. So there are many offshoots from this paper, at least another 3 that I'm concurrently working on. So here's the induction argument. So if G has, and it really comes down to the first one subcase is basically Dirac's argument, right? If G has one more vertex and one more edge, then K3n minus 4. Then similar to Dirac's proof, you get this graph, right? And that's actually, when I was doing Dirac's proof, I saw this one here. And that's when I realized that, that was also applicable in this result. And subcase 2b, when G has one more vertex and 3 more edges, you get exactly one graph. And coincidentally, it's the same. And therefore, there is just one more infinite family. And I believe that is the end. And you can find my book on Amazon. And I promise you that Tutt's theorem is written correctly in my book. Okay, so that's it. Thank you very much.
All right, thank you. Any questions?
Yeah. Sandra? It's just, and again, matroids is your area, so I'm asking. But when you say 4 connected graphs and then you're talking about Tutt, I think about how 4 connected planar graphs always have a Hamiltonian cycle. Is there any sort of like matroid analog for the Hamiltonian cycle idea there?
I haven't worked on the matroid analog of Tutt's. It's Tutt's result that 4 connected graphs have a Hamiltonian cycle. I was actually working with a student on that result and extending it. I know someone who has done some work on Hamiltonian cycles and matroids, but it's really quite a wide open area, and it's a good one to get in. Yeah, so yeah, there's a paper, Almost Planar Graphs, and that's all about Hamiltonian cycles and pancyclicity, and we mentioned Tutt's result, and actually it grew out of Tutt's result, so that's on my webpage. But yes, I think that 4 connected, matroids with Hamiltonian cycles, or what it would be is circuits of size R plus 1. That would be the analog, as in, the largest size of a circuit is the rank plus 1. So a study of matroids with circuits of rank R plus 1 would be good to undertake and see how many if and only if conditions, not if and only if, not happening, if sufficient conditions and necessary conditions you can come up with. Yeah. Now, the structure theorems. So recently there's been some results on extending these operations to 4 connected and how to extend them. And there's some nice papers that are out, and I can send them to you if you're interested. And that is also the area of structural results for 4 connected graphs. I have seen some results on it, but nobody has turned it into an algorithm to actually use them. So another wide open area that's definitely worth looking into.
Cool. Thank you.
Thanks. I feel, I'm sorry, I feel like this talk would be better on the board, you know? There's something about this area that makes it a little bit hard to, especially with a PowerPoint, I mean, a Beamer slide like this. Yeah, maybe the next one I'll give it on the board. Any other questions?
Questions? All right. If not, let's thank the speaker again, and I'll stop the recording.
Thank you for coming. And what happened with that TUTS result? I just got turned around. I don't think that's correct, right? What I wrote? That is bugging me so much.
All right, I'm going to stop the recording, okay?
Oh, it's
Yeah,
not.
yeah.
It's not. I thought